Thank you very much, Pascal. I mean, thank you for this invitation. Of course, I would have liked to be there in person, but so we have to take this as a substitute. Now, I put a very generous title, which means that, you know, I could talk for many hours, but actually, I will be rather specific. I mean, so of course, you know, it's connected to this issue of generalized hydrodynamics, but there will be more talks on the topic, which was sort of widely arranged by the organizers. And so presumably there will be sort of more introductory type material. So I will actually talk about one very specific case, namely the nonlinear Schrödinger equation in one dimension, which is a particular, you know, well-studied integrable classical many-body system, but I want to sort of investigate its hydrodynamic scales. Okay, so let me just sort of put here sort of, you know, the general thing. So it's, as I said, I mean, introduction, you have to wait for other talks why this is an interesting thing to do, but let's just focus our attention to this nonlinear Schrödinger equation. Psi is a complex valued wave field, and of course, when you would quantize that system, I mean, then you get the Lieb-Liniger model, and so therefore, you know, it might be interesting actually to also study the classical counterpart. So I'm interested in a hydrodynamic situation, which means that I want to confine the system. So, you know, this I can just do by periodic boundary conditions. So that's very different from a scattering situation where everything sort of eventually moves to infinity. So here, because the system is confined, if you waited long enough, eventually you would think that, you know, you reach, let's say you start with some sort of more or less arbitrary, randomly chosen initial condition. You would think that in the long time limit, you go to some stationary state, which I sort of call later on sort of natural stationary state, and then you sort of stay there for a long time. Okay, so I want to look at random initial data. So I'm far away from the ground state. The energy will be proportional to the volume. And, you know, this is what usually people call highly excited states. But they are not completely arbitrary. So in the next slide, I will tell you, you know, what kind of highly excited states I'm actually thinking about. And as I said, the main interest is the long time behavior. Now, of course, you know, there are many issues on the long time behavior, but one interesting idea is that if you wait long enough, I mean, there should be sort of like a closed equation on, I mean, what I call Euler scale. I mean, so Euler scale just means that I'm looking at ballistic scaling, so space and time are sort of the same order in natural units. And what you expect is sort of like, you know, sort of a conservation type of equation. So you have ddt of some density is sort of given as the spatial derivative of some current. And of course, what these densities are exactly, we don't know, but, you know, just sort of want to remind you of an ideal gas. Then, of course, the W would be simply the local velocity. And that would be sort of, you know, the usual sort of, you know, free evolution equation, which I would write down. And of course, the V effective is simply just the ordinary velocity. So in this case, we know this system very well. And now somehow the hope would be that if you look at more complicated system, but still integrable, that you have a similar type of equation. Now, of course, at the moment, we don't really know what the meaning of the W is. You know, it's maybe something like a velocity, but it's not clear at the moment. And also, you know, in the simple ideal gas case, I mean, you know, it's just the velocity. So things for each W, you have an independent equation. Now, you know, because it's still an interacting system, you know, the V effective will be some complicated functional locally, means that, you know, for fixed xt, the V effective will be some completely sort of complicated functional of, you know, what this local row of W. Okay, so this we have to figure out, but that's sort of somehow the goal in which I'm proceeding. And just to remind you that, you know, this is not totally obscure. Let's look at sort of, you know, the very rough idea. So the first idea is that you somehow there should be sort of naturally space-time stationary measures. So that's what I said. If I start with random data, wait it long, then you get something which the system sort of approaches in the long time limit. And now the idea is to sort of go to the hydrodynamic scale. That you build now a non-stationary measure but still assuming that locally it's stationary. So here's sort of a canonical ensemble on the macroscopic scale. maybe I have some variation in the local energy, but when I enlarge and sort of see actually the microscopic sort of the wave field microscopically, then I see something which is sort of stationary in space-time, at that particular macroscopic space-time moment. And now sort of the general assumption is that this local stationary is actually propagating in time, and therefore you can hope that you can write down sort of closed equations. And these are the hydrodynamic equations. And on the level of, the Euler equations, all what you have to do is, basically you write down an evolution equation, which on the ballistic scale sort of is an evolution equation for the parameters which label the stationary states. So, these are many words, but of course, it's very familiar. If you look at the one-dimensional fluid, then we know that generically only the number, momentum, and energy are conserved fields, and therefore the Euler equations is a coupled system. Is a coupled system for hyperbolic conservation laws, and so, since we have three components, there will be, it will be a system of three coupled hyperbolic conservation laws. In order to write this actually down, you need something about the thermodynamics of your system. You have to know equation of state. You have to sort of maybe know, what the pressure is, in order to write down the correct Euler equations. And now somehow the idea would be that this kind of procedure also works for integrable systems. So of course, this V must be somehow replaced by some formal infinity. I have a whole extensive number of conservation laws, and so presumably, rather than having three coupled, you will have sort of infinitely many coupled conservation laws. But before even writing down, we have to understand a little bit better what is the generalized free energy for that system, which now depends also on an infinite number of chemical potentials. And so, this is sort of the way I want to work. So actually, most of the talk will be concerned with figuring out what is the generalized free energy. And then of course, once I have this, then I can write down Euler equations and investigate them, but that's sort of part for some future talk. Okay, so now we want to sort of look a little bit at this generalized free energy. And of course, the way you do that, so the way to do this is, formally at least, is that, of course, it's a well-studied system, so you have a list of local densities for the conservation laws. So it starts with the number and momentum and then energy. And the way you construct the generalized Gibbs ensemble is that you simply keep going the list, which you can find in the literature. And then you integrate this over your volume. This gives you the total quantity, which is actually doesn't depend on time. And from this, according to Gibbs, you just put this up in the exponential. There's some very formal a priori measure, which is sort of, the product of the Lebesgue measure at each point in your continuum. And that somehow, is your candidate about which you're thinking. Now, this formula is already a little bit complicated, and maybe something can be done, but that's not the way how I will proceed. Rather, rather than looking at this object, which is at the moment at least a little bit untractable to me, is that you realize that life becomes much simpler if you start discretizing this equation. And so I've written down for you the discretized equation. Sort of, you do the totally naive thing. This is just a discretized Laplacian, and here I have the same nonlinearity as I had in the first slide. It's just exactly the same cubic nonlinearity in the evolution equation. Now, as always, if I just discretize naively, then the result will be a non-integrable system, and therefore it's no good use. We want to study, after all, integrable system. But that's to me still a surprise, but it's a matter of fact that for most of these continuum integrable systems, you have some sort of lattice version which maintains the integrability. And that, in the case of the nonlinear Schrödinger equation, was invented at the high time of integrable systems. Classical integrable systems was discovered by Ablowitz and Ladek. And, the idea is extremely simple. Rather than taking the field exactly at the lattice point J, you just take the sum of the two neighboring lattice points. And that simple procedure ensures you that the system is still integrable. Okay, so now I've written down for you on the next slide the evolution equation for the Ablowitz-Ladek system. So you see exactly the same one I just sort of put here, this particular discretization. And then you realize that, this two you can somehow absorb, and we call the new field alpha. So this is now a complex valued field. And then you rewrite your evolution equation by just combining terms. And I introduce sort of, so alpha is now the complex wave field. I mean, that's just Ablovitz-Ladek notation. And then there's a prefactor which comes from this term and also this term. And you see that it has that very particular structure, and the rho j turns out to be 1 minus alpha rho j squared. I emphasize, maybe I didn't do this before, that I'm looking at the defocusing case, which means that I have here a plus sign, which is sort of, physically the stable case. There's also the focusing case, which is the unstable case, where I put here a minus sign. About this, I don't know anything, and so it's very important that I keep here the right sign. Now, when you look at this expression, then you see that you somehow want to have this to be positive, so that I can take square roots and things like this, and therefore the natural phase space is simply at each side in the complex plane the unique disk. So all the complex numbers which are less than 1. Okay, and then we put periodic boundary conditions. And then we put periodic boundary conditions. So that's just the standard way.
Herbert, may I ask one thing?
Yes.
Is it important that is in this defocusing case for the time evolution?
Well, I mean, yes, I think physically, the time evolution will be very different in both cases. Of course, people have studied all these things, and it just makes a big difference. I don't know whether there is actually even a general.
No, but my question was, it doesn't matter that is unstable.
Well, I don't know. I mean, I just don't know. I mean, it's not clear to me whether there is a sort of a reasonable generalized hydrodynamics for the focusing case.
Okay.
All right. So now we do the conserved fields. Now, of course, Ablovitz-Ladek sort of found already conserved fields, but they wrote it in a way which is totally inappropriate for our purposes. I mean, of course, it's a list and you have some sort of generating function, but I simply don't know how to, wouldn't know how to do anything with this kind of list. I mean, of course, it's there, but I cannot do the next step.
Can I ask a stupid question?
Yes.
How do you go from the equation for psi to the equation for alpha?
Oh, I just removed the 2 here. I mean, that's all.
Okay, that's just change
and then you combine the term. You see, this is plus. I mean, minus psi j minus 1 psi j plus 1. You have the same term here. You just combine, and that gives you the rho j squared. Is that okay?
What's alpha?
Alpha is I removed this phase factor, so now I use the alpha is just the complex wave field. Okay.
Okay, thanks.
It's just I mean, I just removed this fastly oscillating, this oscillating factor which comes from the 2, right? And so it's a trivial, but this is the way how everybody writes it down, and so that's why I'm using this notation, right?
Thanks.
Okay. All right. So now I wanted to say that the standard way how people write down the conserved fields, I don't know what to do with it. I mean, in the sense that there are the conserved fields, but these are complicated formulas which I cannot work with. And so fortunately, Alvina Nenshu, I mean, she discovered sort of another way of writing down this evolution equation, which basically means that she discovered a good way to write what people call the lax pair. So I will explain this in a second, but let me just sort of go a little bit more slowly. I mean, first thing is the system is Hamiltonian. So here you have the Poisson bracket, but it's a weighted Poisson. I mean, so you see this factor here appears, behind the standard sort of Poisson bracket type thing, right? So then you want to know whether this is a Hamiltonian evolution equation. Well, you better write down the Hamiltonian. The Hamiltonian is just quadratic in the alphas, and the bar is here always the complex conjugate. And the complex conjugate, so that's a very simple bilinear form. I mean, it's just sort of what you naively would think, but doesn't lead to linear equations because I have this rho j squared. And when you figure, if you plug it in, you work out this equation, then you find that you get exactly that evolution equation. So that's our Hamiltonian. All right, and now you have this local conservation laws, and of course, conservation law basically means that I have some quantity on phase space, which is now just sort of the n-fold product of the unit disk. So each complex variable is sort of an absolute value less than 1. It just commutes with the Hamiltonian, and so this would be conserved. But we are looking not only for objects which commute or which have zero Poisson bracket, but we really would like to have them at density. So since this, in this audience, I should not emphasize, but let me do it anyhow. You see, I really would like to write the global field as a sum over the densities. And then I'm using this notation, which of course everybody in this audience knows, but let me just sort of, for the sake of clarity, repeat this. You see, if I take a Q0, which is, let's say, some polynomial, alpha minus 1, alpha 1 squared, and both Q squared, that would be one particular example. And then if I put the index j, it just means that I'm shifting to the lattice side j. So it's the same function, but of different, with different arguments. So, I mean, with different labels of the arguments which are going into the definition. Okay. So this is the notation which everybody knows in this audience. And so I just want to make sure that everybody understands my notation. So this means that these QJs are actually, it's just not any family. It's a family which is sort of related by this simple shift operation. Okay, so now we have sort of know what is, and now now the beautiful thing which people discovered in the 70s is that if you are able to write down sort of like a Lex pair, and you will see in a second how this works, then then you find actually a particular operator whose eigenvalues are the conserved quantities, and that's something with which you can work. And so I have to give you sort of this little exercise here on linear algebra, which are the so-called CMV matrices, which only deal, only give you a nice representation, it's sort of a manageable representation of the conserved field. So let me just sort of briefly go to this exercise. So the way how you do it, you think of like, so n is even. And you should think of pairing the system into pairs. I mean, so this is the first pair, the second pair, the third pair, etc. And now at each little pair, I have a block matrix which is 2 by 2, and the 2 by 2 block matrix is sort of constructed in this way. I mean, so this is the alpha, I mean the wave field, and this is this rho j, which is square root of 1 minus alpha squared, right? And so you see, this is lattice side, let's say 0 and 1, and then what I have to put in here is the variables referring to 0, and then I have here 2, 3. Then it would refer to the variables which have here the index 2. Okay, so this is how I construct the matrix Ln. So it's block diagonal in little 2 blocks, and of course it's a total trivial matrix to check that it's unitary, and that cannot be good enough. But now the trick is that you define exactly the same matrix, but you shift the blocks by 1 unit. I mean, this in a quantum community, like most of people, presumably you are in that community. I mean, that's a very familiar thing which people use all over the place, that, in order to produce an interaction, you just shift by 1 lattice unit. So let me call this matrix Mn, and now the Lex matrix is simply the product of the two. This is now, of course, a complicated matrix. Well, it's not so complicated. It's sort of 5 diagonal, but clearly, I cannot simply diagonalize it or anything like this. But what I know is that it's unitary. So the eigenvalues of this matrix are sitting on the unit circle. Okay, so here's.
But it's 2 minutes. It's 2 minutes to the 20 minutes.
Okay. Okay. So So I have to hurry up a little bit. Okay, fine. So this is block diagonal thing, and maybe I cannot. Maybe I cannot go through this construction, but I just want to tell you that the conserved quantities which have a density are simply the trace of the nth power of that matrix, and it's that quantity which is sort of easy to work with. Okay, so I have to sort of do this a little bit more quickly. So now you can sort of construct all these conserved quantities, and then you can sort of write down your a priori measure. So let me maybe just switch to that particular formula. Now I've just written down exactly what I was supposed to do, namely I have an a priori, which is sort of a simple product thing, and then basically I have sitting here, what before was sort of the sum over all conserved quantities becomes now this particular matrix, some arbitrary function of that matrix, and then taking the trace. So this is the formula for the GGE. Okay, and now you see that it has 2 labels. One of them is the pressure, which sort of tells you, it's sort of the analog of the density. I mean, it sort of tells you how this a priori mate is sort of, either very close to the origin, or maybe it's sort of close at the border of your unit disk. And then there's simply a weight according to Boltzmann. Okay, so the thing which I want to emphasize, the Gibbs state has now two labels. One is the pressure, which is a scalar, and the other one is a function, which I call the confining potential. All right, so now comes sort of the most important thing. The rest, we can then switch to the discussion. I want to give you sort of, what is now the correct way of thinking of this new quantity and the correct way of thinking about the hydrodynamics. So you see, what you do is imagine that you sort of evolve your system, and if you want to do hydrodynamics, you have to separate in slow and fast degrees of freedom, and this is how it's magically done through what I call the Lex filter. So you look at your local region, and then you have your wave field, but out of the wave field, I mean, you construct this CMV matrix. And then you look at the eigenvalues, and then you look just at the density of states, and which is just the eigenvalues which are living on the unit circle. And then I put a delta and normalize by 1/n. So that's something which is normalized to 1. Okay. And now the idea is that so here is sort of the picture. When you look in your space time, then locally you have some GGE, but it's actually characterized by the density state and the parameter which is dual to the pressure. And so now the claim is that this construction actually divides into slow degrees of freedom and fast degrees of freedom. And it's the density of states which solves the hydrodynamic equation. I'm not going to write it down, and I have no time anyhow, but the main point is that the quantity which I alluded to in the beginning has actually the meaning, it's the local density of state. So the W is sort of this parameter which tells you that the local density of state, and of course, the local density of state is living on the unit circle. All right, so this was a little bit fast, but nevertheless, I think, I mean, you somehow got the message. But then, there's sort of a positive thing. You might think, this is sort of just mathematical exercise. But the point is that if I give you the Gibbs measure, I mean, there's a variational formula, which of course, everybody in this field might have expected, but there's a variational formula for the density of state. And for this, you have sort of look at this sort of mean field type of free energy function. You see this logarithmic interaction here. So it's sort of like what you know in random matrix theory, sort of the CUE log gas. I mean, okay, so these are charges sitting on the unit circle. And then the claim is that if I take the minimizer of that functional and then I do sort of these funny derivatives, I mean, then I get the local density of state. I should emphasize that there's sort of a, it happens. I mean, you produce, you think you're the only one in the world, and then somebody else sort of independently does sort of more or less the same thing. So actually, we posted sort of more or less at the same day. I mean, without knowing of each other. I mean, they observed also this case. I did sort of a few things more, but they deserve just as much credit as anybody else. Okay, fine. So I just wanted, this slide is just telling you that there is actually a free energy from which you can get this. I mean, there's a variational principle which allows you to compute this density of states. And now once you have, once you look at the minimizer of this free energy functional, then you get to what people know as TVA equations in generalized hydrodynamics. And so, much of the structures which you have in the quantum mechanical systems actually reappear here. Okay, so let me just sort of close here with the last slide. I mean, so that's sort of, I call this discussion and outlook. So one thing which is actually very curious is that you can also do what people call the modified KdV by this mechanism. And the idea is that you look at sort of the imaginary part of your Hamiltonian and also put the minus sign in terms of the quadratic part, and then you put a minus I to make it real, and then you get this particular evolution equation. So that's now very different from the nonlinear Schrödinger equation. It has no similarity. But you realize that if I take alpha initially real, then it will stay real because all these are real quantities. And so sort of things behave somewhat differently because all the algebra still works. You still have your CMV matrices, all the eigenvalues, the conserved quantities. I mean the eigenvalues of the Lex matrix are on the unit circle, but now you have an extra symmetry because this is real, and therefore once I know that e to the I theta is an eigenvalue, then also its complex conjugate is an eigenvalue. And so there's an extra symmetry. And if you come from random matrix theory, I mean, you might guess already what is happening. And indeed, it does happen. I mean, what happens is that rather than having the circular unitary ensemble as your variational problem, you switch to the orthogonal ensemble. Okay, so that's sort of a curious thing. And so actually this analysis gives you sort of another example which has sort of a somewhat unusual structure, but you know, the general scheme of generalized hydrodynamics is still working. Okay. Now continuum NLS, I said already, that's sort of a riddle. I mean, I just want to mention sort of this analysis of the Sinch-Gordon equation by De Luca and Musado, and also Benjamin and Yoshimura and others, I mean, which sort of investigated that particular case. And so, you know, maybe that would give you a guiding line to actually understand the continuum. Anyway, so thank you very much for listening.
Benjamin, do you want to go ahead and ask your question?
Yes. Sorry,
Yeah.
I got disconnected for a second. Ben, yes, you raised the hand, please ask.
Yeah, no problem, thank you. Yeah, Herbert, so just a quick question. In this equation that's even on your slide now with the rho square is 1 minus alpha square. But could you consider outside the unit disk instead of inside? I mean, I know the two are disconnected, but could you consider what happened outside?
Yeah, I don't know. I mean, I simply don't know. You see, the point is that algebraically, you know, writing down the conserved quantities, I mean, you know, as long as you just do the algebra, you don't see any difference between whether it's plus or minus. Okay? Yeah. So if you want to know about, you know, let's say, you know, and formally, of course, the eigenvalues are still conserved. And so if you just do the formal thing, you don't see any difference. But the first moment where the difference really appears is that when I'm asking myself, you know, can you say anything about the spectrum of this operator? And then you realize that once you put, you know, if you go outside the unit disk, I mean, you lose unitarity.
Yeah. Yeah.
And then okay, so then at that moment, I just don't know what to do. I mean, actually, it was one of the things which you know, sort of, I always have sort of people who sort of collaborating and they want to do numerical simulations. I thought it would be an interesting thing to actually just look at this operator directly and see what the spectrum looks like. I mean, that might be quite informative, but it hasn't been done. And that never goes so quickly as you would like to. But yeah, no. I mean, this is the point where you know, I mean, the algebra, you know, works perfectly. Yeah. There's which you would expect somehow, you know, because it's really algebra, and how could the algebra discover the difference between plus and minus? I mean, that's right. It's the unitarity which breaks down, and then I'm stuck.
Thanks, Herbert. Are there more questions?
Can I ask a question quick? This is the defocusing case, is that right?
That's a defocusing case, yes.
So, have you thought about the focusing case?
Well, that's what I was trying to say. I mean, yes, I mean, I have been thinking, but I cannot give you any positive feedback. I mean, in fact, you know, I mean, so what is known from numerical simulations directly of the nonlinear Schrödinger equation, of course, that you know, the defocusing and focusing behave very differently. I mean, the defocusing is sort of, everything is rather stable. If you go to the focusing case, I mean, you sort of, you know, you see clustering. I mean, maybe you form solitons which are moving in a particular way, and all kind of things. And so it's clear that you know, from a dynamical point of view, you know, the two systems sort of look rather differently. And so, but that's all I can say at the moment. Yeah.
Thank you.
Are there other questions? Okay, I have one question. It's just if I take the continuum limit of this equation,
yes,
do I recover the same classical limit of the quantum nonlinear Schrödinger equation?
That's a very good question. I mean, yeah, I'm thinking about this. I mean, this is right. I mean, well, I mean, what you you know, there's something called the Sakharov-Shabbat equation, for classical integrable systems, and you know, one conjecture would be that you sort of recover that. I mean, this is a very good remark. You know, I'm thinking about it. You know, I don't have anything definite at the moment, but it's a very valid remark. I mean, you might think that, in fact, you see, you might think that you know, just taking the continuum limit of this Ablowitz-Latex thing, I mean, you should get sort of a rather solid information about the hydrodynamics of the continuum system. Yes, no, I think that's a very good remark. Yeah. Mm-hmm.
Okay. Okay, actually the time just half an hour finished now, so I think we can thank Herbert again, and we can move to the next speaker, which is Ben, if I remember correctly.